So Green's theorem. So where we're coming from, where we're taking a step from, is the fundamental theorem of line integrals, and then also we previously did the vector version, fundamental theorem of calculus and its vector version, the fundamental theorem of line integrals. So what that did was it gave an equation between the integral of a derivative expression over a line, which is one-dimensional, and then evaluating the original expression, the original function, at the line's boundary endpoints, which are zero-dimensional. So those two formulas look like this. So now what we're going to do is we're going to do two things. First of all, we're going to find the relationship between a two-variable function, for two-variable functions, between integral over a two-dimensional graph and integral over a one-dimensional graph, which is, of course, a line. So the way that we do that is we start by saying, well, what if C itself is the boundary? And then C is now a boundary of a two-dimensional region. And then we also need what is the proper derivative expression that we're going to be taking the integral of. And since we're in two dimensions, the integral expression is going to be swirl. So what we wind up with is this. So the double integral over region R is the swirl of the vector field F dA. That double integral equals the integral over the curve of vector field F dot dr. So, and with the assumptions that vector field F is f of xy, it's two-dimensional, it's smooth, meaning you could take any derivative you like, and it's continuous. And then the curve C is, the one-dimensional curve C is a boundary for a two-dimensional region R. So this can also be written out in coordinates using x's and y's. So if you do that, and then also remembering that f is going to be, we'll call it the two coordinate functions p and q. So we could write this out as either of these things. So then written out in coordinates, the swirl is just going to be dq dx minus dp dy. And then f dot dr, after you take the dot product, it's p dx plus q dy. So then put it all together and you get this equation written out in, so you can either write it in coordinate-free version, the first one, or using coordinates, which is this version. Okay. So what does Green's theorem do? Well, typically the line integral is hard to calculate, but the double integral is relatively easy. Sometimes it's the other way around. So let's take a look at an example. So calculate this line integral, the integral over the path C of x minus y dx plus x plus y dy, where C is the circle centered at the origin with radius 2. So how do we do this? Well, first let's go through the old painful way. Let's calculate it directly as a line integral. So how do you do that? Well, first you got to make your parameterizations. So the radius is 2, it's centered at the origin, therefore x equals 2 cos t and y equals 2 sine t. We can calculate dx equals negative 2 sine t dt, and dy equals 2 cos t dt, and t goes from 0 to 2 pi. And then, of course, we've got the parameterization for f, so let's just plug it all in. So you get, so plug in parameterization into the integral from 0 to 2 pi of 2 cos t minus 2 sine t times negative 2 sine t dt plus 2 cos t plus 2 sine t, all of that times 2 cos t dt. Collect all the terms and then everything times dt. And you get these 4 terms. And let's see, oh, the first and the last term cancel. That's really nice. And then the middle 2 terms, 4 sine squared t plus 4 cos squared t, that just becomes 4. So it's actually simplified kind of nicely. We got lucky. So then you just get 4t evaluated from 0 to 2 pi. And so the answer is just 8 pi. Okay. But now let's use our new method, Green's theorem. So note that C is a closed path. It's a circle. Therefore, we can use Green's theorem. So let's take a look. So note that the vector field implied by this problem is P comma Q, which is X minus Y, comma X plus Y. So now we can use Green's theorem either in the coordinate form or the coordinate free form. So remember, in coordinate form it looked like this, and in vector form it looked like this. So I prefer vector form. Let's do it that way. So the swirl of this vector field, Q is X plus Y, so dQ dx is 1. P is X minus Y, so dP dy is -1. Swirl is 1 minus -1. The swirl is just 2. Therefore, the line integral is just the double integral over the region of the swirl, which is 2 dA. Now this simplifies really, really nicely because 2 is a constant, so we can just factor it out. So you get 2 times the double integral over the region of dA. And we know that the double integral of dA just means the area of the region. The area of the region, it was a circle radius 2, so that's just pi times 2 squared, which is 4 pi, times the constant 2, and you just get 8 pi. So in this case, I showed you both the old method, doing it by hand, and the new method using Green's theorem, and they both worked. That won't always happen. Let's take a look. So here's an example. Calculate the integral over the curve of x squared cos x dx plus e to the y cos y dy, where C is the circle, radius 1, center of the origin. So let's see what happens if we try to do it method 1, calculate directly as a line integral. Well, C is a circle. We know the parameterization for that. X equals cos t, y equals sine t. And we can get dr calculating dx and dy. Now, plug that in, and what happens? Plug in your parameterization for your vector field f, plug in your parameterization for dx and dy, and you get, and sorting it out, you get this. The integral from 0 to 2 pi of cos squared t times cosine of t, all that dt, and then e to the plus e to the sine t times cos of sine of t times cosine t dt. Yikes. It is not clear how to do that integral. Fortunately, with Green's theorem, we don't have to. Since C is a closed path, we can use Green's theorem. So the integral over the curve of this expression is just equal to the double integral over the enclosed region R of swirl of f dA. So now we just got to find swirl of f. So notice that the implied vector field, the first component is x squared cos x. The second component is e to the y cos y. What's the swirl? Looking at q, dq dx is 0. Looking at p, dp dy is 0. So guess what?
0.
The swirl is 0, therefore the double integral is 0, therefore the answer is 0. Done and done. So now, as a side comment, let's take a lesson from that. Look at what Green's theorem tells us about a conservative vector field.
Is equal to 0.
So, well, two things have to be true. If the swirl is 0, then we know that
Positive.
It's a conservative vector field. So, looking at Green's theorem from that point of view, the vector line integral over the curve C of f dot dr is just the double integral over the region of swirl f dA. That's just the swirl of the gradient of f, function f, which we know by one of our identities that we showed, that's always 0. So in words, what does that say? It says the line integral of a conservative vector field over a closed loop must be 0. Now, we already saw that. That was already a result of the fundamental theorem of line integrals, but now it's also a result of Green's theorem. They both tell us the same fact. So we know that line integrals can be used to calculate work. So let's talk about this in the context of doing work. Okay, so find the work done by the force F equals cos y minus y, comma negative x sine y, to move a particle once counterclockwise around the rectangle with these corners. So just really quickly, here's the picture on the right, so you see what's going on. And we know that work is this line integral. Okay. So as always, we know there are two ways to do this. We know there's one way to do this line integral, which is old-fashioned by hand from scratch. So I'm just going to mention that can be done. It's quite a pain because since the curve is a rectangle, there's four linear sides, and each of those linear pieces you have to calculate with its own formula and do all that up. So I'm just going to throw that calculation up on the screen just so you can see it and remember that that's a thing that we could do. It's kind of irritating, so we don't want to do it. But it turns out we don't have to do it. Why don't we have to do it? Since C is a closed path, we can use Green's theorem. So we know that work is the line integral. It's our vector line integral, but this vector line integral, since C is a closed path, by Green's theorem, it's just the double integral over the region of swirl of f dA. So now we got to go ahead and calculate. So the swirl of f is dq dx minus dp dy. So dq dx is negative sine y, and then dp dy is minus sine y minus 1, subtract, and you just wind up with 1. So this is just the double integral of 1 dA. But of course, that's just, since that's a constant, you could factor it out, or it's 1, you could ignore it. That's just the area of the region. And it's a rectangle. And if we go back and check out the rectangle, you can see that one side goes from x equals 2 to x equals 5. That side is length 3. The other side, y equals 1 to y equals 7. That length is 6. So 3 times 6, the area is just 18, and that's your answer. Okay. So when C is a closed loop, and you can use Green's theorem, this can be very, very helpful in terms of simplifying what's going on. So I believe you might be wondering, what happens if swirl does not just give you a constant? Let's take a look. So let's repeat the last problem, but with a slightly different force field. So now let's say the force field is cos y minus y, comma 0.5x squared minus x sine y. So I've tweaked it. So we're going to do the same. C is still that rectangle. So we know that it's a closed loop, so we can use Green's theorem. So work is the vector line integral. And because C is the closed loop, we can just use Green's theorem. It's the double integral over the region of swirl of f dA. So swirl of f, if we calculate it now, dq dx gives us x minus sine y, dp dy is negative sine y minus 1. calculate and simplify, and you get x plus 1. So now we actually got to do it. So this is the double integral of x plus 1. And we know, because it's a rectangle, we already know what the boundaries are. X goes from 2 to 5, and y goes from 1 to 7. And the boundaries are constant. You could set it up either way. So I chose to do it dy dx. So integral with respect to y, it's just y times x plus 1, plugging in y going from 1 to 7. And you just get 6 times that, so 6x plus 6. Now integrating from 2 to 5, you get 3x squared plus 6x as x goes from 2 to 5. So plugging it in, subtract, you get 81. So even if the swirl is not a constant, in this case, you get a relatively straightforward double integral that you can do pretty much no problem.
Professor, quick question.
And yes, since it's work, we should put joules. Okay. So at this point, let me make a general observation. So if you have the vector line integral, the integral over the curve C of vector field f dot dr, you now have 3 different ways that you could approach doing that integral. So what we just learned is that if C is a closed path, we can use Green's theorem. What you've previously seen is that if the vector field f is conservative, then you can use the fundamental theorem of line integrals. And then if neither of those conditions are true, then it's just a vector line integral, and you just do it, calculate by hand using parameterization, blah, blah, blah. Okay. So ideally, you hope that one of those 2 things is true. It makes the problem very easy. If neither of those things is true, you just have to go ahead and calculate. Okay. Next, I want to look at a math application. So in this case, we're going to use Green's theorem to calculate the area. So things are going to change up a bit in how we apply it. Let's take a look at what I mean by that. So find the area enclosed by the ellipse, x squared over a squared plus y squared over b squared equals 1. Yeah. So, so how do we do this problem? So we're trying to find the area. So we know that in general, the area of a region is the double integral over R of dA, and I'm sticking a 1 in there for a reason. So it's just double integral over the region R of 1 dA. So, and by the region R, of course, we mean the interior, the area enclosed by the ellipse. Okay. So in this case, in this problem, we're actually starting with a double integral. And the hint is that we're going to use Green's theorem in order to convert this into a line integral. So this is, in a sense, going backwards from the way that we normally go. But in order to do this, we need some vector field f. So in other words, 1 has to be the swirl of some vector field f. So we need some vector field f whose swirl is 1. Which vector field f are we going to use? Any vector field whose swirl is 1. Now, there are tons of possibilities. But what I want to do is I want to use the one which, hint, hint, is going to make our calculations work out the easiest. And I'm going to give it to you. So the vector field we're going to use is this one right here, negative half y, comma half x. So quickly you calculate the swirl, you get dq dx minus dp dy is half minus negative half, which is 1. So here is the thing that we want to do. We know that the area is the double integral of 1 dA, which is going to be the line integral of this, f dot dr, which is going to work out as negative half y dx plus half x dy. And again, C is our ellipse. So we know how to parameterize the ellipse. We did it in a previous problem, but just to remind you, it's like a circle, but x and y each have their own coefficients. So in this case, x equals a times cos t, and y equals b times sine t. And t goes from 0 to 2 pi. And once we have that, we can now just do our regular line integral calculation. So we need the parameterization for dr. We can calculate dx and dy. Dx is negative a sine t dt. Dy is b cos t dt. And now let's plug in all the parameterizations. So the area is just going to be the integral as t goes from 0 to 2 pi. Plug that all in, you get negative half b sine t times negative a sine t dt plus half a cos t times b cos t, all that dt. So let's collect everything. So this gives half ab sine squared t plus half ab cos squared t and all of that dt. And now this is why I chose this specific vector field. Looking at this thing that we need to integrate, clearly it simplifies very nicely, because it worked out exactly like this. You factor out the half AB and sine squared t plus cos squared t equals 1. So now we just need to do this single integral, which of course is very easy. Half AB is just constant, so half ABT as t goes from 0 to 2 pi, multiply it out, and you get, or plug it in and you get pi AB. So this was a sort of case, doesn't typically happen, but this was a case where the double integral was kind of the hard thing to do, but the line integral, as it worked out, was the easy thing to do. So we use Green's theorem in that direction. Usually it's going to be the other way. We want to do a line integral, which is hard, but Green's theorem will make it easy. So I want to give you a little bonus bit right here. And the bonus bit is an alternate form of Green's theorem. So I just want to throw this out there. We're not really so much going to use this version of Green's theorem now, but it's going to be useful. This idea is going to be useful for us later on. So I want to sort of emphasize that I'm teaching this to you with really more so in mind with stuff that's going to happen down the road. So understanding that, let's take a look at a different form of Green's theorem. So first of all, remember that when we talk about our curve C, it's r equals x of y, but r x comma y, but it's a function of t. So r of t is x of t comma y of t, and t going from a to b, and that's the boundary of some region r. So we know that we can talk about a tangent vector. So remember that the tangent vector is just dr dt, which would be x prime comma y prime. We can turn that into a unit tangent vector just dividing by the magnitude. Let's actually do that first. Okay. So the unit tangent vector we write as capital bold T. And so x prime of t is the first component, but then we want to divide by the magnitude. So when we write r prime of t like that, when r is not bold, again, remember that just means the magnitude. And then the same thing in the second component. We take y prime, and then we divide by the magnitude. So that is the tangent vector divided by its magnitude. So this is the unit tangent. Okay. Now, for our current purposes, we're also going to describe what the unit normal is. So in 2 dimensions, we know how to take a tangent vector and turn it into, turn it into a perpendicular, which would be a normal vector. You switch the components and make the second one negative. And of course, this will still be a unit vector. So you get y prime over, again, divided by magnitude, so y prime over r prime, comma, negative x prime, again, divided by magnitude, so over r prime. So that's a little introduction into what we've got there. And that's generally true. So now let's apply it to our Green's theorem scenario. So I'm going to start with this. We're going to start with the flux line integral. So the flux line integral was, instead of dotting it with the parallel vector, we dot it with the perpendicular vector. Remember that, in a sense, calculates the flow across. So the integral over the curve of f dot n, the unit normal vector, ds. So let's rewrite what all these things are. So we know that ds can be written as dr dt, the magnitude of dr dt times dt. And let's see what all that means. So we know that f is pq, and we know that unit normal n is this thing that we just said. So put that all together and write it all out. Let's see what we get. So dotting vector field f and unit normal n, first you get this bit, so p dot y prime divided by the magnitude of r prime, minus q dot x prime divided by the magnitude of r prime, multiplied by, from ds, the magnitude of r prime dt. Clearly, those magnitude of r prime things are going to cancel out. And when that happens, what you get is p dot y prime of t dt minus q times x prime of t dt. Well, so y prime is dy dt, and then that's times dt. So what is that? That's just p dy. And similarly for the second piece, that's just minus q dx. So if we sort this around to put the dx part first, which is what we're used to, you get the integral over the curve of minus q dx plus p dy. And now we're going to apply our original version of Green's theorem. So the original version of Green's theorem says take d dx of the second thing and subtract d dy of the first thing. So notice that the swirl, so the vector field is negative q comma p in this case. So the swirl of negative q comma p is dp dx minus negative dq dy. So that just tells us this is equal to dp, the double integral over the region of dp dx plus dq dy, and then all of that dA, by applying the old version, applying the original version of Green's theorem. So if we write it fully in vectors, dp dx plus dq dy is actually something that's a form of something that we know. That is actually just the divergence of the vector field f. And this gives us an alternate version of Green's theorem. And again, the important thing is, notice that in this case, we're starting not with the dot product with dr, which is parallel to the curve, but we're starting with a dot dn in the line integral, which is perpendicular to the curve. So again, this is just an alternate version of Green's theorem, dealing with what happens if we do instead of the regular vector line integral, what happens if we think about the flux line integral. So not motion parallel, but motion perpendicular to the curve. And it turns out to be the double integral of the divergence when we do that way. Okay. So again, I want to emphasize that you should think of this as a bonus version of Green's theorem. We're going to come back later on to using this in a helpful way. And now, as a bonus, let us, oops, where is it? Ooh, where did I put it? Sorry. Okay. Here we go. Let us, sorry, let me make this a little nicer. Okay. So let us look at the special case where we're going to do a proof of Green's theorem now. We're only going to consider the special case where the region is a rectangle. It would be possible to do this in a little more generality, but I just want to give you an idea for what the proof would look like, and I'm using the rectangle because with a rectangle, the boundaries of integration are constants. That'll just make things a little easier as we go through the proof. Okay, so proof of Green's theorem in the special case where it's a rectangle, where the region is the region or the curve is a rectangle. So here's how it goes. So the first thing, so I want to say, ignore all the calculations as you're about to see. I just want to show you the image, which is the rectangle on the right side. So sorry about that. Hold on. Okay. So actually, you know what? Instead of doing that, let me actually just draw it. So drawing it, what are we talking about here? So here is the region. So there's the curve C. And I'm saying that X goes from A to B and Y goes from C to D. And I'm going to name each of the four sides. So I'm going to say the bottom side is B for bottom. On the right, it's R. On the top, it's T. And on the left, it's L. So those are my names for my four pieces. Okay. So let us start out by doing the line integral around that path for some vector field F, which is P comma Q. So the line integral written out in coordinate form is the integral over the curve of P dx plus Q dy. So now let's break it up into let's break the curve up into the four pieces, B plus R plus T plus L. So because there's four pieces, and then the integral itself has a dx part and a dy part, that's going to break the integral up into 8 pieces. So I'm going to write all the p parts, all the p dx parts first, and then all the q dy parts at the back end. So let's now think about how that breaks down. So notice that on the bottom, on the bottom piece B, X is changing, but Y is constant. So if Y is constant, dy is 0. So along the path B, dy equals 0. So that's 0. So we're going to get rid of it. And we can do this 4 more times. On the right, and that's also true on the top part T. Again, along the top, Y is constant, therefore dy is 0. That gets rid of that piece. Along the right piece, X is constant, X equals B, therefore dx equals 0. So right piece dx is 0, so that's 0, that goes away. And along the left piece of the rectangle, X is constant, therefore dx is 0. So that piece also goes away. So that leaves us with just these 4 pieces. Okay. Next, we need to actually translate what these things are. Now we're going to write it out. So notice that along, for example, along the bottom piece, y is constant. So p isn't really just some general function. It's actually it's not just a function of x, y in general. It's a function of x comma c, since y always takes the value of c. And then in the second integral, the integral along t of p dx, along the top part, y always takes the value d. So we can say that p is just a function of x comma d. And then also notice that along the bottom part, x goes from a to b. And then along the top part, since we have to consider the orientation, this is a path after all, notice that going along the top part, x goes from b to a, because you have to follow the direction of the orientation of the path. Okay. Similarly, for the other two integrals, along the right part of along the right path, notice that x is always constant, x is always the value b. So q is really not just q of x, y, but it's q of b comma y. X is constant there. And also, along the right path, so the third integral is along the right path, y is going from c to d. And then along the left path, as we follow, x going, y is going from C to D. And along the left path, because we have to follow the direction of the arrows, the orientation of the path, y is going from D to C. So we have to respect that as we set up the boundaries for the integral. Okay. So now just to simplify talking about stuff, I'm only going to follow down, I'm only going to explain for now the second two integrals, in other words, the q dy integrals. So looking at just those two. So I want to make all my integrals from c to d. So on the last integral, I want to switch the boundaries. But when, of course, when you switch just the boundaries, then you also switch the sign of the integral. So that just happened right there. Okay. But now that I've got two integrals with the same boundaries, I can just combine them. So this is the integral from c to d of q of by minus q of ay, and then all of that dy. Now here comes the fancy step. So what does this remind us of? This is the function q with b plugged in minus some function q with x equals a plugged in. So this looks almost as if we had just done an integral. So the thing is, we have to figure out, what did we just do the integral of? Well, we had to integrate with respect to x, so that we're now going to plug in values for x, a and b. So what, when we integrate with respect to x, is going to give us q? That's got to be dq dx. So notice that the integral from a to b of dq dx, all of that dx, is just going to give us the original function q, and we're going to plug in x equals a and x equals b and subtract. So that gives us the thing that we had before. And that is just using the regular fundamental theorem of calculus. That's the key step. Okay. Now, something very, very similar happens over on the other side with the p dx integrals. Of course, the difference is that we've plugged in constants. So switching back over to this side, we've plugged in constants for y. So therefore, we're going to need to have a dp dy and then integrate with respect to y. Now something else weird happens, which is that because of the way the integral is set up, in order to make it the integral from c to d, there winds up being a negative in front. And that just happens if you just keep track of which way things go. And the effect on the orientation. But all in all, finally, we've got the thing that we want. So now we just combine these two integrals. So now we've got the integral as x goes from a to b, as y goes from c to d, of qx minus py, and of course, now we know that that's just the swirl, and now that is the proof of Green's theorem just on the special region of a rectangle. So a quick review. So what's Green's theorem? Green's theorem says for a smooth two-dimensional vector field f of xy, where when closed path C is the boundary of the region R, you get this: the line integral, vector line integral over C of vector f dot dr is just the double integral over the region swirl of f dA. We can also write this out instead of using vectors, but rather using coordinates. And then that would give you the version double integral over the region of dq dx minus dp dy, all that dA equals the line integral over the curve of pdx plus qdy. And then finally, as a sort of bonus, we got Green's theorem in an alternate form, which says that the integral over the flux line integral over the curve of f dot unit normal n ds, that's equal to the double integral over the region of the divergence of f dA. But again, we're going to focus mostly on the original or main version of Green's theorem. And then the typical way that we use Green's theorem is when we've got a line integral that we're trying to do. If once we identify that C is a closed path, then we can apply Green's theorem.